You've probably heard about the recent failures in lunar exploration. The headlines appeared briefly, then vanished into the scroll of daily news. Another rocket, another crash, another crater on the moon. But do you know that a successful soft landing on our satellite was achieved as far back as 1966? That's not a typo. 1966. When men still wore fedoras and computers filled entire rooms. When the Soviet mission, Luna 9, accomplished what seemed utterly unthinkable. It touched down on the lunar surface, remained intact, and began transmitting photographs back to Earth. Before that moment, every single attempt had ended the same way. Metal screaming against regolith, a burst of debris, silence. A grave marked only by a new scar on an already ancient, cratered world. But Luna 9 changed everything. It proved that the moon's surface could support weight, a question that had paralyzed scientists for years. Some theorists genuinely believed the surface was meters-deep powder that would swallow any lander whole like quicksand. Luna 9 shattered that nightmare. It sat there, stable, and stared up at the sky above the ocean of storms for 3 days, whispering its data back to a world that had held its breath. The story didn't begin in 1966. Go back to 1959, when Luna 2 became the first human-made object to reach another world, smashing into the lunar surface at over 3 kilometers per second. Not a soft landing, but a declaration. We are here. Humanity had touched the moon for the first time, even if only through a cloud of vaporized metal. That single event drew a line across history, before and after. Before, the moon was mythology. After, it was a destination. The space race ignited with a ferocity that still seems almost surreal in retrospect. Two superpowers, separated by ideology and mutual terror, both pointing their rockets at the same pale disk in the night sky. And for a few extraordinary years, it seemed like anything was possible. Now fast forward to August 2023. Russia attempted another soft landing with Luna 25. The spacecraft had traveled 384,000 kilometers. It had survived launch, the vacuum of deep space, and the transition into lunar orbit. And then, in the final moments, the moments that matter most, it crashed. Luna 25 added itself to the moon's growing collection of human wreckage, a new scar among thousands of old ones. This feels deeply strange. Technology has advanced to an almost incomprehensible degree since 1966. We have quantum processors, machine learning, and reusable rockets that land themselves upright on drone ships in the middle of the ocean. We carry in our pockets devices with more computing power than the entire Apollo program combined. And yet, we crashed. Again. Some will blame politics. Budget cuts, brain drain, institutional decay after the collapse of the Soviet space program. And there is truth in that, but it's incomplete. Because Russia was not alone in failing. In April 2023, a Japanese private company called iSpace crashed its Hakuto-R lander into the lunar surface. Not a government agency. A private company backed by modern venture capital, using 21st century engineering, built in a country whose reputation for technological precision is essentially legendary. Japan makes bullet trains that arrive within seconds of schedule. And yet, the moon swallowed their lander whole. Before that, India's Chandrayaan-2, 2019, an extraordinarily ambitious mission that executed flawlessly for months, until the final 2.1 kilometers. The lander Vikram dropped in radio silence, making contact with the surface at a velocity it was never designed to survive. India's engineers had done everything right, and then the moon said no. Why? Why has landing on the moon become so extraordinarily difficult? Why does the 21st century, with all its silicon and algorithms and billion-dollar budgets, struggle to do something that Soviet engineers did with slide rules and vacuum tubes in 1966? The answer is buried in the physics of the moon itself, and the deeper you dig, the stranger and more hostile this world becomes. The moon's gravity is lying to you. Let's start with something that sounds deceptively simple: gravity. On Earth, gravity is your constant companion, utterly reliable, boringly uniform. You know exactly how hard the ground will pull you, whether you're in Tokyo or Toronto, on a mountaintop, or in a valley. Gravity keeps its promises. The moon does not keep its promises. Lunar gravity is a patchwork of anomalies, lumps, and invisible inconsistencies. The technical term is mascons, mass concentrations. Regions where enormous amounts of extra mass sit beneath the surface, creating gravitational fields measurably stronger than their surroundings. These mascons were first detected in the 1960s by early lunar orbiters, whose trajectories would gradually shift in ways that confounded mission controllers. The spacecraft weren't malfunctioning. The moon was misbehaving. The most dramatic mascons sit over ancient impact basins, the great circular scars left by asteroid impacts billions of years ago. When a massive rock from space punches into a world, it doesn't just excavate a crater. It reshapes the mantle beneath and sometimes draws up dense material from deep inside in a slow geological rebound, leaving a concentration of unusually dense material just below the surface, pulling at anything that passes overhead. In 2019, scientists made a particularly stunning discovery. Beneath the South Pole Aitken Basin, the largest, deepest, and oldest impact crater on the moon, they detected a mass of material estimated at approximately 2.18 times 10 to the 18th power kilograms. That's roughly 2.18 quadrillion metric tons, an amount of extra mass so vast it bends the moon's gravitational field in ways that challenge orbital mechanics. Yes, some corners of the internet immediately began whispering about buried alien spacecraft. But the leading scientific hypothesis suggests this is a remnant of the ancient impactor itself, an asteroid so enormous that when it struck the moon billions of years ago, much of its iron core didn't vaporize. It sank, embedding itself deep within the lunar mantle, where it has sat ever since, a hidden ghost of a cosmic collision that helped shape the early solar system. The South Pole Aitken Basin is 2,500 kilometers across and up to 8 kilometers deep. If placed on Earth, it would cover most of the United States. This is not a geological feature. This is a catastrophe frozen in time. And what this means for spacecraft descending toward the South Pole is that the gravitational field in this region is profoundly irregular. A descending craft is not falling through a smooth, predictable environment. It's navigating an invisible obstacle course of gravitational pulls, each one capable of nudging the trajectory by fractions of a degree. Fractions that, by the time the spacecraft reaches the surface, translate into hundreds of meters of error. Miss the flat landing zone by 200 meters, and you're descending into a boulder field, a crater rim, or a permanently shadowed pit where the temperature is colder than the surface of Pluto. This is why engineers spend years modeling the moon's gravitational field. This is why missions still fail. The moon's gravitational complexity is not a problem that has been solved. It has been managed, imperfectly, provisionally, with constant risk of catastrophic surprise. Why the moon is harder to land on than Mars. Here's a paradox that will rewire your intuitions. Mars is easier to land on than the moon, not in every respect, but in the specific engineering challenge of getting from orbit to the surface in one piece. The red planet offers something the moon doesn't. It offers air. Mars has an atmosphere, thin, about 1% the density of Earth's, but there. And that thin veil of carbon dioxide is enough to change everything. When a spacecraft enters at orbital velocity, the air pushes back. Friction slows the vehicle dramatically. By the time a Martian lander has descended through the atmosphere, It has already lost most of its velocity before deploying a parachute. Then come the parachutes. Even in Mars's thin air, a large enough parachute slows a vehicle dramatically. Curiosity, landing in 2012, used a parachute nearly 21 meters in diameter. Perseverance, in 2021, did the same. These parachutes gave the spacecraft precious seconds, time to make calculations, time to activate descent engines, time for onboard computers to find a flat spot using terrain relative navigation. Ingenuity, the small helicopter that flew more than 70 times before its final landing, would never have reached Mars without that atmospheric assistance. The Moon has none of this. Zero. The lunar surface sits at the bottom of pure vacuum. No aerodynamic drag, no parachutes, no heat shields for deceleration. A spacecraft arriving from lunar orbit travels at roughly 1.6 kilometers per second. The only thing that can slow it down is rocket engines. Every single meter per second of velocity must be burned away using propellant. The descent is a precisely choreographed sequence of engine burns, each one calculated to reduce speed by a specific amount at a specific altitude. There is no margin for error, and the communications delay makes real-time human intervention impossible. Radio signals take about 1.3 seconds to reach the Moon. Round trip, 2.6 seconds. If a mission controller sees something going wrong and sends a corrective command, 2.6 seconds will pass before the spacecraft even receives it. In the final moments of a lunar landing, 2.6 seconds is an eternity. The difference between a successful touchdown and a smoking crater. This is why lunar landers must be smart enough to land themselves. The software guiding a lunar lander must account for every conceivable scenario: dust-obscuring sensors, unexpected slopes, gravitational anomalies, engine deviations, and make the correct decision in milliseconds. Getting this software right is extraordinarily difficult. And then there is the human factor, or rather, its absence from robotic missions. The Apollo program carries a single astonishing statistic. Not one mission lost a crew member during the actual landing. 6 missions. 12 astronauts descended in lunar modules. Every single one touched down safely. This is more remarkable than it sounds. Apollo 11 is the most famous example. As the lunar module descended, the onboard guidance computer began issuing alarm codes. Mission controllers determined the computer was overloading but functional and gave the go to continue. Then Armstrong looked out the window and saw the problem. They were headed for a crater the size of a football field, its floor strewn with boulders large enough to tip the lander. Armstrong took manual control. With fuel depleting at a rate that left approximately 25 seconds of hover time remaining, he flew the lunar module over the boulder field, found a clear spot, and set it down. His heart rate hit 150 beats per minute. Mission controllers in Houston stopped breathing. And then, almost impossibly, the Eagle has landed. No autonomous guidance system has ever duplicated that performance. Human judgment, experience, and intuition under extreme stress saved that mission. The robot equivalent of Neil Armstrong doesn't exist yet. And that is one of the deepest challenges in modern lunar exploration. The South Pole, the most valuable and most dangerous destination. The geography of lunar ambition has shifted dramatically since the Apollo era. Armstrong and Aldrin landed in the Sea of Tranquility, vast, relatively flat, near the equator. Subsequent Apollo missions chose similar terrain, accessible, predictable. But no modern mission of significance wants to go there anymore. The lunar South Pole is where the action is. It's where Chandrayaan-2 crashed in 2019, where Luna 25 crashed in 2023, where Chandrayaan-3 successfully touched down in August 2023, making India only the 4th nation to achieve a soft lunar landing, and the first to do so at the South Pole. It's where NASA's Artemis program intends to send humans, where China is planning a research base. Why? One word: water. The floors of many polar craters have never seen direct sunlight, not in billions of years. In these permanently shadowed regions, temperatures drop to around -200 degrees Celsius, or colder. Water ice accumulated from ancient comet and asteroid impacts has been preserved there, frozen in place for geological ages. Water is not just water on the moon. It is oxygen for breathing, hydrogen for rocket fuel. It is the difference between a base that requires every kilogram of life support hauled from Earth at tens of thousands of dollars per kilogram, and a base that can sustain and potentially refuel itself. The South Pole could be the gateway to the entire solar system, a fueling depot, a waypoint, the first permanent human settlement beyond Earth. But the South Pole is also, from a landing perspective, a nightmare. The permanently shadowed regions that make it scientifically valuable are pitch dark, no solar power, temperatures that destroy standard electronics in minutes. The nearby areas that do receive sunlight are on crater rims and elevated ridges, where terrain is rough and sloped. Landing on a slope means the lander tips, solar panels face the wrong direction, and the mission ends. The trajectory to reach the South Pole requires a polar orbit, a significantly different approach than the equatorial trajectories that made Apollo landings relatively simpler. Polar orbits require more complex three-dimensional navigation. The approach geometry is less forgiving, and the extreme contrast between blindingly lit ridges and utterly dark crater floors confuses optical navigation systems. This is the challenge that defeated Luna 25. The challenge that claimed Chandrayaan-2, and the challenge that India's Chandrayaan-3 team, chastened by failure and energized by necessity, spent 4 years learning to overcome. Their success is one of the most significant engineering achievements in recent spaceflight history, not because it was glamorous, but because it was hard, and they did it anyway, on a fraction of NASA's budget, with lessons bought through public failure. The lessons of history. From Ranger to Apollo to now, we have been here before, not just in the sense that humans landed on the moon 6 times between 1969 and 1972. We have been here in the sense of failure, of repeated, expensive, embarrassing failure, followed by dogged persistence, incremental learning, and eventual triumph. The Ranger program is the archetype. Between 1961 and 1965, NASA launched 9 Ranger spacecraft toward the moon. Of the first 6, 5 failed before accomplishing their mission. Rangers 1 and 2 never escaped Earth's orbit. Rangers 3, 4, and 5 either missed the moon entirely or hit it without returning usable data. Ranger 6 made it to the moon and impacted precisely on target, but its cameras had been accidentally switched on during launch and were destroyed by solar radiation before they could function. 6 consecutive failures. Congressional hearings were held. Careers were threatened. The program was nearly canceled. And then Rangers 7, 8, and 9 worked perfectly, returning thousands of close-up images that transformed humanity's understanding of the moon and laid the groundwork for Apollo. The Surveyor program followed. 7 spacecraft sent to demonstrate soft landing capability. 5 of 7 succeeded. Then Apollo. 12 men walked on the moon. A technological achievement so improbable it still seems like mythology. And yet it happened through exactly this process: failure, analysis, iteration, improvement. The program didn't succeed despite accepting failure as a possibility. It succeeded because it understood failure as an inevitability to be prepared for. Now, 60 years later, the same arc repeats in the new lunar rush. Chandrayaan-2 failed, Chandrayaan-3 succeeded. Japan's iSpace crashed in 2023. They launched a second mission in 2024. The American CLPS program sent Peregrine Mission 1 in January 2024. It suffered a propellant anomaly, but transmitted valuable data before its mission ended. Intuitive Machines IM-1 landed in February 2024, tipping over but still returning science, the first American soft landing since Apollo 17 in 1972. These are not failures in the damning sense. They are steps. Awkward, expensive, sometimes fatal steps, each one carrying knowledge that the next mission will use to do better. The moon has not become harder to reach. We have become more ambitious about where we're trying to go and what we're trying to do when we get there. The Apollo equatorial landings were relatively forgiving compared to South Pole precision landing in permanent shadow terrain. We are raising the difficulty level because the stakes are higher, and we are learning, imperfectly, painfully, how to meet that difficulty. What it would actually feel like. The human body on the moon. But let's stop for a moment and think about something rarely found in engineering postmortems. What would it actually be like to be there, not to send a robot, to live there? To wake up on the moon every day, breathe recycled air, and watch Earth hanging in a sky that is permanently and utterly black. Start with gravity. The moon's surface gravity is approximately 1.62 meters per second squared, about 16.5% of Earth's. You would weigh roughly 1/6 of your terrestrial weight. This sounds pleasant. The Apollo astronauts seemed to enjoy it, bounding across the surface in those iconic slow-motion leaps. But the human body was not designed for 16.5% gravity. It was designed over millions of years for exactly one gravitational environment, Earth's. Bone density is perhaps the most immediate casualty. The human skeleton is a dynamic structure, constantly rebuilt in response to mechanical stress. When you walk and run under Earth's gravity, you stress your bones, and that stress stimulates bone-building cells. In low gravity, that stress disappears. Bones begin to deteriorate. Astronauts on the International Space Station lose approximately 1 to 2% of their bone mass per month, with hours of daily resistive exercise specifically designed to counteract this. On the moon, the situation differs from microgravity, but is not dramatically better. Muscle mass follows the same pattern. The cardiovascular system recalibrates. Fluid redistribution shifts toward the upper body, potentially affecting intracranial pressure. Recent research has raised particularly alarming concerns about vision. A significant percentage of long-duration ISS astronauts have returned with structural changes to their eyes. Spaceflight-associated neuroocular syndrome, or SANS. Intracranial pressure increases in reduced gravity, pushing on the optic nerve and deforming the eye itself. Several astronauts have returned from long missions with permanently degraded vision. The immune system changes in ways not fully understood. Viral latency, the ability of dormant viruses to reactivate, increases in spaceflight environments. In the confined, high-stress environment of a lunar base, with limited medical resources, this is a genuine clinical concern. And then there is the question of psychological sustainability, not just survival, but the maintenance of mental health, social cohesion, and cognitive performance under conditions of unprecedented isolation and confinement. The prison of the sky, psychological dimensions of lunar living. The Antarctic winter over analogy is instructive. Every year, small teams of researchers spend the Antarctic winter at stations like McMurdo, 8 months of isolation in extreme cold, confined to a few small buildings as the outside environment tries to kill them. This is perhaps the closest terrestrial analog we have to a lunar base. What happens to people in these environments is well documented. Early enthusiasm, gradual adjustment, a midwinter low, sometimes called the winter over syndrome, characterized by depression, irritability, sleep disruption, cognitive slowing, and social friction. Long-term psychological effects that can persist after return to normal society. In Antarctic stations, at least there is Earth gravity. There is a 24-hour day-night cycle. There is the possibility, however remote, that a medical emergency might eventually be evacuated. On the Moon, none of these safety nets exist. The lunar day is approximately 29.5 Earth days, 2 weeks of sunlight followed by 2 weeks of darkness. Human circadian rhythms, evolved for a 24-hour cycle, would face a fundamental mismatch. Artificial lighting can help, but its effectiveness in preventing cascading circadian disruption is partial at best. Communication with Earth carries a 1.3-second one-way delay. Under normal circumstances, barely noticeable. Under stress, a medical emergency, a mental health crisis, an interpersonal conflict, the delay becomes psychologically significant. The conversation rhythm is broken. You are aware, at every moment, that Earth is far away, and the people who might help you are separated by that vast, dark gulf. Submarine crews offer another analogy. Nuclear submarines spend months underwater, crew living in a metal tube under enormous psychological and physical pressure. Crew selection, training, and culture are all specifically engineered to manage the effects of prolonged confinement. Even so, conflicts arise, performance degrades, mental health problems occur, and submarine crews can always surface. They are never truly isolated in the existential sense that a lunar crew would be. The view from a lunar base window would be simultaneously magnificent and deeply alienating. Earth hangs in a black sky, beautiful, blue, heartbreakingly far away. The landscape outside is gray, dead, and utterly unchanging. No seasons, no weather, no life, no movement except the creeping shadows as the sun slowly tracks. Day after day, week after week, the same gray world, the same black sky, the same distant blue marble that contains everyone you have ever loved. History's long-duration expeditions consistently report that the hardest thing is not the physical danger, it's the relentlessness, the absolute sameness, the inability to escape. You can't go for a walk outside. You can't feel wind or rain. You can't smell anything except recycled air and your own confined humanity. These are not trivial challenges. They are potentially mission-critical. The invisible killer, radiation on the Moon. The Earth's magnetic field is a miracle we take completely for granted. Invisible, silent, and utterly essential to life, the magnetosphere deflects the constant stream of charged particles ejected by the sun and redirects catastrophically energetic particles from solar flares and coronal mass ejections. It is a force field, one that makes the difference between a habitable planet and a sterile rock. The Moon has no such protection, no global magnetic field. The lunar surface sits exposed to the full fury of space radiation, unshielded, unfiltered, and utterly merciless. There are two primary radiation threats. The first is chronic exposure to galactic cosmic rays, high-energy particles arriving from outside our solar system, produced by supernovae across the galaxy. These particles are extraordinarily penetrating, capable of passing through meters of rock. They cannot be practically shielded against using any material we currently know how to build with. Every person on the lunar surface will absorb a continuous dose, day and night, regardless of where they stand. The second threat is acute exposure from solar particle events, flares and coronal mass ejections that can increase radiation levels at the lunar surface by factors of hundreds or thousands within minutes, with little warning. A major solar particle event during an unshielded spacewalk could deliver a lethal dose of radiation in hours. Underground habitats, burying living quarters under meters of lunar regolith, are among the most seriously proposed solutions. The regolith provides shielding similar to dense rock. Lava tubes, ancient underground channels some hundreds of meters in diameter, are being seriously studied as potential habitation sites, offering natural radiation shielding with minimal construction effort. But spacewalks will still be necessary. Science will need doing. Science doesn't happen from inside a buried bunker, and every exposure accumulates. over years, over decades. The long-term health consequences include not just cancer, but cataracts. The Apollo astronauts showed elevated rates correlated with cosmic ray exposure, cardiovascular disease, and neurological effects only beginning to be understood. Recent research has raised alarming possibilities about cognitive decline associated with galactic cosmic ray exposure, raising the prospect that radiation may damage neural tissue affecting memory, decision-making, and personality over time. The moon is trying to kill us in ways we can't see and can't feel. You cannot sense a cosmic ray passing through your brain. You cannot feel the DNA damage accumulating in your cells. The radiation doesn't care about your ambitions or your courage. The dust that never stops. Of all the challenges of lunar living, none is more insidious or underappreciated than the dust. Lunar regolith, the broken and powdered rock covering the surface to depths of several meters, is unlike any earthly soil. On Earth, rock particles are rounded and smoothed by water, wind, and biological action. They have been tumbled against each other for millions of years. They are, in a sense, domesticated. Lunar regolith has never been domesticated. Formed by billions of years of micrometeorite bombardment and cosmic ray processing in a place with no water, no weather, and no life, lunar dust particles are jagged, angular, and microscopically sharp. They are also electrostatically charged, clinging to surfaces with extraordinary tenacity, and in some conditions levitating in clouds above the surface. Apollo astronauts were tormented by it. The dust-coated spacesuits crept into joints and seals, abraded visors, clogged filters, and worked into cabin environments despite meticulous care. Harrison Schmitt, Apollo 17's geologist, developed what he described as lunar hay fever, sneezing, watery eyes, a sore throat, from dust that made it into the cabin. The symptoms faded after a day, but Schmitt was exposed to lunar dust for only 3 days. Imagine years. The toxicological properties are genuinely alarming. Laboratory studies using simulants have found that fine lunar regolith particles, when inhaled, cause significant inflammation in lung tissue, comparable in some studies to the damage caused by crystalline silica, one of the most hazardous occupational lung hazards known. The freshly broken crystalline surfaces of lunar dust particles are chemically reactive in ways that terrestrial dust particles are not, having never been exposed to oxygen or water before entering a human lung. Long-term exposure could plausibly cause progressive pulmonary fibrosis, a scarring of lung tissue that reduces respiratory capacity and has no cure. Dust also attacks equipment. Abrasive particles work their way into every mechanism: bearings, seals, optical surfaces, solar panels. The Apollo missions were short enough that dust damage was a nuisance rather than a mission-ending failure. Long-term operations would face progressive degradation of virtually all mechanical and optical systems. Solar panels would require frequent cleaning to maintain power output. Spacesuits would need replacement as dust abraded through their outer layers. The cascade. How risks multiply. One of the most important concepts in risk analysis for human spaceflight is the cascade, where one failure triggers a chain of consequences that amplifies and compounds into a situation far more dangerous than any single problem. Think about what happens if a solar particle event strikes a lunar base during a spacewalk. The crew is outside maintaining equipment. A solar flare erupts with perhaps 15 to 30 minutes of advance notice. The crew must immediately return to the habitat, but their suits are covered in dust. The decontamination airlock takes several minutes to cycle. During those minutes, the crew absorbs radiation. Once inside, one astronaut shows early symptoms of acute radiation sickness: nausea, headache, fatigue, requiring medical attention, consuming crew time, medical supplies, and psychological energy. Meanwhile, the equipment left outside during the emergency abort sits unattended. The task being performed, perhaps critical maintenance on the life support system, is incomplete. The incompletely maintained system now has a higher failure probability. All of this is happening while the crew deals with the aftermath of a radiation emergency, psychological stress elevated, communication delay making Earth-based medical consultation agonizingly slow. This is a cascade. One event, a solar flare, has triggered a chain involving radiation exposure, dust contamination, medical emergency, maintenance failure, psychological stress, and communication limitation, all interacting simultaneously. The same cascade logic applies to almost every lunar risk. A micrometeorite strike on a habitat module doesn't just cause a pressure leak. It triggers emergency protocols, requires a spacewalk to assess damage, exposes crew to dust and radiation during that walk, consumes emergency oxygen reserves, and creates psychological trauma affecting crew performance for weeks. A failure of the water recycling system doesn't just create a logistical problem. It forces resource rationing decisions, creates interpersonal stress, and potentially forces an early mission end, requiring another dangerous spacewalk to prepare the habitat for uncrewed storage. Each individual risk on the moon is serious. The cascade interactions make the true picture dramatically worse. Robots, the honest answer. Given everything above, the obvious question is, why send humans at all? Why not just send robots? It is a reasonable argument, and it deserves an honest examination rather than a reflexive defense of human spaceflight based on sentiment and inspiration. Robots are already doing remarkable science on planetary surfaces. Opportunity, designed for a 90-day mission, operated on Mars for nearly 15 years, covering over 45 kilometers of terrain. Curiosity, still operational after more than 12 years, has climbed Gale Crater's central peak and found compelling evidence of Mars's ancient habitability. Perseverance is collecting samples for eventual return to Earth. Ingenuity completed over 70 flights before its final landing. These are genuine achievements. The science is real. The engineering is extraordinary. And no human has risked their health to accomplish it. But robots have fundamental limitations that in certain contexts are not minor inconveniences, but mission-critical constraints. Opportunity's 45 kilometers in 15 years works out to an average pace a human walking with moderate difficulty could cover in an afternoon. Every single movement had to be carefully planned, uplinked, executed, and verified. Human geology field teams cover more ground in a day than Opportunity covered in years. The 24-minute round-trip communication delay to Mars means even a nominally autonomous rover cannot respond to real-time scientific opportunities the way a human geologist can. When a field geologist notices something unexpected, a mineralogical anomaly, an unusual rock texture, they stop, look more closely, take a sample, adjust their investigation in real time. A rover requires hours or days to execute the same pivot. Scientific opportunities that a human would capture in minutes are lost. The honest answer is that robots and humans are not competitors, but complements. Robots excel at routine, repetitive, long-duration tasks in environments too dangerous for sustained human presence. Humans are essential for adaptability, complex problem-solving, tasks requiring judgment and creativity. The path to a permanent human presence on the moon probably runs through an extended period of robotic preparation, robots building infrastructure, mapping resources, testing systems, followed by human missions that leverage that groundwork. This is what NASA's Artemis architecture nominally envisions. Whether it will be executed with the consistency and funding it requires is a separate, mostly political question. The backup planet illusion. There is a narrative that has gained significant traction in popular space discourse. It goes like this: Earth faces existential threats: climate change, asteroid impact, pandemic, nuclear war. Therefore, humanity must become multiplanetary. We must establish self-sustaining settlements on the Moon and Mars so that when catastrophe strikes Earth, human civilization survives. The Moon, in this framing, is a lifeboat. It is emotionally compelling. It draws on deep human instincts about survival and the cosmic significance of our existence. But the narrative contains a foundational error. The Moon and Mars are not survivable without constant, sophisticated technological support that itself depends entirely on Earth. A lunar base in 2030 or even 2050 will require a continuous supply chain: food, spare parts, electronics, medicines, specialized materials. The technology to produce all of these from lunar resources does not exist and will not exist for decades at minimum. A lunar colony in the near-term future is not an independent civilization. It is a very expensive, very fragile outpost that would perish within months if the supply chain from Earth were severed. The scenario in which a lunar base serves as a backup for Earth is precisely the scenario in which the base cannot survive. A catastrophe severe enough to threaten human civilization on Earth would also sever the supply chains, communication links, and manufacturing capabilities that a lunar base depends on. If Earth's industrial civilization collapses, the lunar base dies too. The backup is not independent of the system it is supposed to back up. Terraforming offers a theoretical escape, transforming the Moon or Mars into an environment where humans can live without technological life support. But the Moon's physical characteristics make terraforming not just difficult, but arguably impossible. The Moon has insufficient mass to gravitationally retain a thick atmosphere. Any atmosphere we might create would gradually leak into space. The Moon rotates too slowly for an Earth-like climate system. The lack of a global magnetic field means any atmosphere would be continuously eroded by the solar wind. These are not engineering challenges to be overcome. They are fundamental physical constraints imposed by the Moon's mass and position. The case for lunar exploration doesn't need the backup planet narrative to be compelling. The scientific case, understanding planetary formation, searching for signs of past life, is compelling on its own terms. The resource extraction case, water ice as a local resource, potential helium-3 for future fusion reactors, is real and growing more concrete. The technological development case, technologies developed for deep space exploration, have consistently generated value for terrestrial applications, is well established. But dressing these legitimate justifications in the clothing of existential necessity is intellectually dishonest. It may ultimately harm the cause it intends to serve by creating expectations that reality cannot meet. And by displacing attention from the existential challenges we have the power to address here, on the planet we actually live on, if we choose to do so. The philosophy of the pale gray dot. Carl Sagan, standing before a photograph of Earth taken by Voyager 1 from beyond Neptune's orbit, spoke some of the most important words in the history of scientific communication. That image showed Earth as a pale blue dot, less than a pixel, hanging in a beam of scattered sunlight against absolute blackness. His meditation was a call to humility, a reminder that on the cosmic scale we are, as he put it, a mote of dust suspended in a sunbeam, and that everything we are and have ever been plays out on that single tiny world. If you were standing on the Moon, Earth would appear roughly 4 times larger than the full Moon appears from Earth. Large enough to see continents, weather systems, the blue of the oceans. Beautiful beyond description, this luminous marble hanging in black infinity above a gray and desolate horizon. And yet everything you have ever known, everyone you have ever loved, every place that has ever meant anything to you, it would fit within a disk smaller than your fist held at arm's length. The Moon teaches something that Mars, despite inspiring rhetoric, cannot teach as viscerally, that Earth is not just our home, but our entire context for meaning. The moon is close enough that Earth remains visually present, large and glorious and heartbreakingly real. It is far enough that the distance carries weight, that the fundamental otherness of this gray, airless world, compared to the living blue one overhead, is unmistakable. The purpose of going to the moon is not to leave Earth behind. It is to understand Earth more deeply by seeing it from outside, to expand the context in which we understand ourselves, not just as nations or civilizations, but as inhabitants of a specific and precious world, in a universe vast enough to make that specificity remarkable. The risks of lunar exploration are real. The deaths that future missions will almost certainly cause are real. The human suffering involved, physical deterioration, psychological torment, the isolation and the fear, is real. These are not arguments against going. They are arguments for going honestly, with open eyes, with clear understanding of what we are asking human beings to endure, and with a moral commitment to the well-being of the people we send. We go because curiosity is one of the most profound expressions of what it means to be human. We go because the boundary between the known and the unknown has always drawn us forward, despite the cost. We go because the alternative, remaining safely within the familiar, looking at the moon from a comfortable distance and deciding it's too hard, too dangerous, too expensive, represents a diminishment of the human spirit that no risk-benefit analysis can justify. We go because when Harrison Schmitt knelt in the gray dust of Taurus Littrow and held in his gloved hands a rock that had formed billions of years before Earth's continents existed, he was doing something no robot has ever done and may never do. He was curious, not programmed to collect data, genuinely, irreducibly curious, moved by the strangeness and beauty and age of what he held, present in a way that algorithms cannot replicate. The moon is waiting, not patiently. It doesn't know patience. It simply is, as it has been for 4.5 billion years, indifferent to our ambitions and our fears alike. But we are not indifferent. We never have been. From the first human who looked up at the full moon and felt something stir in the wordless depths of consciousness, to the engineers in mission control who held their breath as Armstrong searched for a flat piece of ground with seconds of fuel remaining, to the ESRO scientists who wept openly when Chandrayaan-3 confirmed touchdown, we have never been able to simply look at the moon and let it alone. That inability is our greatest weakness and our most essential strength. It will carry us there. Broken robots and broken budgets and broken dreams notwithstanding, it will carry us there. And when we arrive and look up from the gray dust at the small blue world above, perhaps we will finally understand both it and ourselves a little better. Stay curious. Keep looking up. And if this video deepened your understanding of just how extraordinary and how genuinely dangerous the challenge of lunar exploration truly is, please give it a like. It helps this channel more than you can imagine, and it tells us that this kind of deep, honest science storytelling is what you want more of. Subscribe to stay with us as we continue to explore the hardest, strangest, and most beautiful questions in space science. We have much more to show you. The universe is far stranger than it appears, and we are only just beginning to understand it. Thank you for watching all the way to the end. The greatest chapter of human exploration is just beginning, and every small step, however stumbling, is a step toward the stars.